everyone. I am Martin Abaldamaro from BSED Math 3D, and today I am here to present the last and final project, project number 6, which is investigating the cosets of all subgroup isomorphic to Z sub n. So, of in looking at all the cosets left and right, as well as the properties of the subset, all the sets that are isomorphic to Z sub n, instead of going at it one by one, I'll just have here an example and then I'll explain it as a whole while I am explaining with the example. So before we start, let us use all the properties that we know. So since we all know that all the J sub n groups are cyclic, we can use the property 3 where G is a generator and G in the order of G. So for example, G is generated by A and G as the order n, where and then if A is a subgroup of G and H has order of D, then D dividing n, then D must divide n. And if there is, instead of K, A divides n, it should be K divides n, D divides. So in here it just says that, for example, D divides n. That means that there is only one subgroup for that order. So I'll go into it in more detail later. So first theory. And so here is another property that we will use. So one, every cyclic group is abelian. So just keep that in mind for now. And another one is every cyclic group is abelian. And another property that we should keep in mind is that all the subgroups of a cyclic group is cyclic. So here is a Jn. So here is a J sub 12. So you can see there is 12. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 12 elements. This is J sub 12 and this is a cyclic subgroup. So for example, our subgroup has an element of 6, an order of 6. So 0, 2, 4, 6, 10. And then again, from property 1, since there are 6 elements in subgroup X, then 6 divided by the total, so there are 12. That is 6 divided by, that is 12 divided by 6. That means 2. That means that 2 is the generator for the 6, for the subgroup of order 6. And there is only one subgroup that has an order 6 here. Now, as you can see, this is the right coset because in here is the right, is the right element. We are operating the element on the right, and in here we are operating the element on the left. So this is a left coset. So why am I saying that? Because every cyclic group is abelian. It means that when you operate from the left, from the right, or from the left, it will be the same. That means that all for a cyclic group, Market to J sub n, all the all the subgroups are normal subgroups. And that means that every single cyclic group must have every subgroup of every single cyclic group must have an upper group. Another one is that so this is as you can see, so there are two subgroups and there are two cosets. The one operated originally and the other is when operated by one. That means that this as an index of 2 because in index you just count the number of right cosets. So you don't count this. This is the left coset. Yeah. So another one is let's look here and look at the element, it's the order of each element. So the order of element is how many times you must operate number by itself to get the identity element. For example, in here, the order of 0 is 0 because 0 is our identity element and 0 operates 0 is 0. So let's try this with 1. So 1 operate 1 is 2, 2 operate 1 is 3. So that's 2 operations. 3 operate 1 is 4, 4 operate 1 is 5, 5 operate 1 is 6, 6 operate 1 is 7, 7 operate 1 is 8, 8 operate 1 is 9, 9 operate 1 is 10, 10 operate 1 is 11, and 11 operate 1 is 0. So we work 11 times. That means that 1 has an order of 11. We can say that. So here, for example, let's uh, let's 6. 6 operate 6 is 0. That means that 6 is one time only. So the order of 6 of element 6 is 1. So with this, we can say that for for a cyclic subgroup, the order we can find the index of each subgroup by the order of each element. So group, so the index of each subgroup is the order of the group divided by the order of subgroup. So for example, this has 12. So the original has 12 elements. And here is it has 6 elements by 12 divided by 6 is 2. And the number of our subgroup is also 2. Another one that we can generalize from what I have shown is that for for every cyclic subgroup, there each each set of cosets and each subgroup and their respective cosets will always be normal because they are abelian. Because for the property one, the average cyclic group is abelian. That is all for operating three. All the operation that is isomorphic to z sub n. I hope that it was clear. Once again, this is Mark B and Abel Damano from the SCD Math 3B. Thank you for listening.